machine learning model, which is what we've done, what we do in DESI, and you teach it, this is what a quasar looks like, this is what a galaxy looks like, and then it can automatically take in a spectrum and classify all the objects. So spectroscopy is very powerful for anything that's kind of beyond the local universe, where all the images kind of just look like this. Oh, and all of this is publicly available. There's this link called the Legacy Survey Viewer, and you can look at images and spectra from the first release of the DESI data. So once I get a spectrum, I like quasars, so we're going to focus on this. Quasar, what can you do? So you can actually get a lot of physics just from this one spectrum. I can measure the continuum. So this is the underlying light, and this is the light from your accretion. So I can measure how many solar masses a year is the black hole eating, so the accretion rate. More importantly, you can measure these emission lines. So these lines are kind of specific transitions and elements, so magnesium 2 and then a couple of carbon lines. And you can measure the width, how bright they are, and you can actually constrain the black hole mass from these emission lines. What I'm doing at the moment in my latest paper is you can tell whether winds are being launched by the black hole, and more importantly, how far away a quasar is. So people will often ask, well, how do you know how far all these random objects are? We can measure these emission lines, and we know the exact wavelength that they should occur if in a vacuum in the lab. We then take the observed wavelength from your telescope, and then we see what's the shift of this emission line observed to rest, and that will tell you the redshift, or how far away it is. So what I showed here is kind of a typical quasar. This is what most quasars look like, and that's what I would call a blue quasar. And it's blue, and this is another example, because as we go to bluer wavelengths, the continuum ramps up, so you get this upward rise. So you get more flux in the blue wavelengths, and that's why a lot of quasars look very blue. I'm more interested, as mentioned, maybe a little bit niche, but hopefully I can see they're important, in these red quasars. So this is an example from one of my papers, and you can see that they look very similar. They still have these emission lines, so slightly lower signature noise spectrum, but the main difference is instead of rising into the blue, we have this kind of drop in flux. And this drop in flux in the blue means that when you look at them in the sky, they appear much redder. Why do they appear red? So we think they're red due to dust reddening. So I've showed a picture of a sunset here. As the sun gets lower in the sky, the sunlight has to travel through more of the atmosphere, so the blue light gets preferentially scattered, and your sunsets appear red. So we think there's similar things happening in red quasars. There's some kind of material that's either absorbing or scattering blue light. And just to reiterate, these are, again, real images. This is a blue quasar, this is a red quasar. In the optical, they just appear blue and red, which is hence the name. So why are red quasars important? Well, since they've been discovered, people were unsure how they connect to blue quasars. And there's two kind of key scenarios. There's the orientation model that's very similar to this unified model of AGN, where we think a blue quasar has an unobscured view of this accretion disk. The accretion disk is very bright in optical and ultraviolet, and so that's why most quasars look very blue. And then maybe a red quasar, you're just looking at it at a slightly different angle. Maybe you look through a bit of this dusky torus, and this little bit of dust absorbs the blue light from the accretion disk, and that's why they appear red. So in this scenario, red and blue quasars are intrinsically the same object, it's just a viewing angle. The other scenario, which is what I've kind of been testing in my research, is the evolutionary scenario. So this scenario suggests that maybe you have two galaxies that merge together. When you merge together, you create one galaxy or supermassive black holes merge, but there's a lot of kind of chaos and dust, and you kind of go through a big starburst phase. You then funnel a lot of stuff into the center. This ignites the quasar because the black hole's eating so much, but there's still a lot of dust left over, and this is your red quasar phase. So there's just a lot of dust in the galaxy. And then through jets or winds, you blow away the surrounding dust and gas, and then you get rid of the dust, and you're left with a typical blue quasar. And then maybe eventually your blue quasar, the centre will run out of material to feed the black hole, and then what we call, it will turn off and become a dormant galaxy. So, in my work, I've been trying to distinguish between these two scenarios. Why this is important is if the evolutionary scenario is correct, then the red quasar is this younger phase in galaxy evolution, and potentially a key phase where the black hole's growing quite rapidly. So if we want to understand galaxy evolution, we might need to consider this red quasar phase. So in the last kind of few minutes, I'll just go through a couple of my key results. First of all, I use some spectroscopy, because I love spectroscopy, and I find that the red colours in red quasars are indeed due to dust. I show this by, in the blue, this is a blue quasar, and this grey line is just a model where I've added a bit of dust, increasing amounts of dust to this blue quasar, and I just see what happens to the spectrum. And then in red are 12 red quasars I observed with the very large telescope, and what you can hopefully see, but it's a bit more quantitative in the paper, is that the shape of these red quasars can be matched quite easily to just a dust red and blue quasar. So I believe that red quasars aren't just blue quasars with some dust, and that's kind of my starting point. So what have I been doing in DESI? Well, because the quasar targeting program is mainly a machine learning model, and it's been trained with blue quasars. So DESI preferentially sees blue quasars. That's what it's been trained to find. So we applied for a program within DESI that's been ongoing to try and target these dust-red quasars that might have otherwise been missed. So this is again the legacy survey viewer. You can spend hours looking at the sky. We zoom into a little patch here. We see, oh, there's a lovely spiral galaxy, which I don't care about. I care about this little orange blob here. This is one of the red quasars that was observed with my program. So, in my paper from a couple of years ago, I take all of this spectroscopy from DESI, looking at red quasars. I then combine this with radio data, specifically from the low frequency array, or LOFAR, which is this radio station in the Netherlands. They look kind of different to your regular radio telescopes, that's because they're lower frequency. And I want to explore the connection between this dust we find in these red quasars and the radio. So this is the key result. There's a lot going on here, but what this is the radio detection fraction. So this is the number, kind of percentage of quasars that I can detect, I can see in the radio, compared to the amount of reddening. So if you go towards the right, this is red, dustier quasars, and then on your left are blue quasars. And here I've included a little cutout of a typical quasar at that reddening, just to show you what the optical images look like, and they do indeed get redder. And what I find is that the more dust you have in a quasar, the higher your radio detection fraction. So the more of them have radio emission. And on the bottom, this is just a kind of, these are composite spectra of what the DESI spectrum would look like at these different levels of reddening. So we find some connection between the dust, which is what's making these quasars red, and the production of radio emission. And this is interesting because radio is not affected by dust. That's why if you have a radio in your house, it's not blocked by your house. Radio waves can pass through anything. So why is the presence of dust affecting the radio emission. So I look into this a bit deeper. I look at radio morphologies. So this is just, what does the shape, if you take a radio image, what does the shape look like? And you can kind of classify them into four kind of key categories. Faint just means it's too faint to kind of say, to know what the shape is. Compact just means it looks like a blob, it's unresolved. Extended is where you see a bit of extension, and then FR2 is just this historical category, which means you see two kind of jets. And in one of my papers, I use high resolution radio data. So this is like, if you need glasses, kind of put your glasses on, you get a sharper image, and so we can really start to resolve these radio morphologies. And what I find is that the majority of these dusky red quasars have very small scale radio emission compared to blue quasars. So they seem to preferentially have radio emission, but on very small scales. So I had a couple of other papers, but I won't go into it, but these results support the evolutionary scenario. Because if red and blue quasars were just intrinsically the same object, it's not clear why they would have vastly different radio properties. But what I think is happening is dusky wind in red quasars. So this is my cartoon, if you can't tell. So these little clouds represent the dust in your galaxy. I think what's happening is the black hole is shooting out a jet or winds, and when your jet or wind hits the dust cloud, it shocks it, and this shock produces synchrotron emission, which is radio. And the more clouds you have, the more likely you are to intercept a wind or a jet. And that's why the more dust you have, the more likely you are to have radio emission. But it's been shown that radio emission due to shocks shouldn't be large scale, because we're not talking about these large scale jets. So this all kind of fits. This is still work in progress, so I'm still trying to kind of test this theory. But if this were correct, this fits in with this evolutionary scenario that as you shock and hit these dust clouds, you're going to heat them up, you're going to destroy them, or you're going to blow them away. And then eventually, if you blow enough away, you'll kind of evolve into a blue quasar, because you've got rid of all your dust. So yeah, that's it. Future work. I'm part of the multi-object optical to near-infrared spectrograph, or MOONS, which is the next generation multi-object spectrograph on the VLT. And it was built in Edinburgh. I think it's still in Edinburgh because there were some issues, but it should be on the sky next year. And as you can see, it looks quite similar to DESI. It has the same kind of robotic fire system. And just briefly, what's great about MOONS is that it pushes into the near-infrared. So this is a simulated quasar spectrum. This in orange is what you can see with DESI, and this is what you'll be able to see with MOONS. So we can push way into the near-infrared, and that opens up a lot of kind of science capability that I don't have time to go into, but it should be great if it ever gets on the sky, which hopefully it will. And yeah, that's all from me. Thank you very much.
Well, thank you very much, Vicky. That was a very clear talk, taking us from a nice gentle start all the way through to your research with just about the right level of mind blowing. I think there should be some element of having your mind blown, so thank you very much. Now, actually, I'm not going to ask you a question. We'll get questions in a minute. First of all, I want to ask the audience question. Hands up if you correctly identified the quasar of those three. Sorry, no, hands up if you didn't identify the quasar correctly in those three images. There you go. And the clever clogs? Who did? Charles. Very good. Okay. So, have we got any questions for Vicky? I imagine you. Yes?
That DESI video you showed with the robotic fibres, is each of those fibres individually imaging a separate quasar, or are they all together?
No, they're individually imaging. So every time you observe, there's 5,000 of them, so you get 5,000 spectra. And so that's how it managed to get so many. And it wasn't like the instrumentation's amazing, but also the kind of, we had a pipeline in place, and the team called it Redshift by breakfast because it's in the US, and basically it takes the observations, it stops, everything's run through the pipeline, it does all the fitting, it gives it a redshift, it gives it a spec type, and by the time the Europeans wake up, you have your latest data from the night before you can access straight away. So yeah, it's pretty great.
But then in 3 years' time, the AI will also do all of your job as well, maybe.
Well, maybe my partner's job, which is writing software, but I'm hoping that research, I'll be, I mean, people are using it. I use it as well. I mean, it's not great for research because it makes up citations. So I'm like finding a paper on dust radio connection quasars, and then it gives me a paper. I search that paper that doesn't exist. So it is useful, but I don't think it's quite there yet. So a lot of people have been testing it, and they're like, it's not. They say it's PhD level intelligence, but I don't think it quite is yet. So, but it will be soon, I guess. Yeah.
Yes?
That was really interesting, thank you very much. Does your evolutionary theory, is that supported by differential distances between the red and the blue quasars? So are there ones that tend to be further away, or would that not apply?
No, that's a really good question. So it doesn't. So for my work, so the further away an object is, because of redshift effects, it appears redder. So you have to kind of take this into account. So what I do is I actually match in redshift. So which means that my blue and my red are like at the same distances, so I don't have redshift effects. So I can't look at that because I include that in my sample selection. In theory, yes, you would see more red quasars further away, and we were discussing there's these little red dots, the James Webb Space Telescopes, observing at really high redshifts that might be like progenitor to red quasars. But that could be done. You'd have to do like a blind survey, fit them all to make sure they are actually quasars, take into account redshift effects in the colour. But yeah, it could be done. I haven't, but I can think about that. Yeah.
Yes?
One open question in high energy astrophysics is the origin of ultra high energy cosmic rays, and AGN are looked at as one potential source for them. Do you see anything in the evolution mechanism or how we created any link to anything which actually could create this cosmic rays?
Yes, that's a really good question, right? Because I have never really considered cosmic rays. I went to a conference 3 weeks ago that was on like AGN and cosmic rays. There was loads of people really interested in cosmic rays, and cosmic rays do produce like radio emission. So they could be important in these AGN, and we've actually just hired a PhD student that's going to be doing simulations of cosmic rays in AGN to see how important they are. Because naively I thought they're not that important just because quasars is, so it's like the central engine that's the most important thing, but going to this conference, they might be important. But yeah, we have a student that should be running simulations on cosmic rays and the radio emission they produce and stuff like that. But yeah, I'm not sure that's...
Historically, it's two different communities. This went from astrophysics and went from high energy physics. So.
Yeah, that's why I realised at this conference is there's people that just spend their whole life obsessed with cosmic rays, and cosmic rays are the answer to everything. So maybe I just never really looked into it myself, but yeah.
Yep.
Jai 313, 1806,
Yes.
most distant one we have seen. He mentioned, well, you put the next slide after that, you can see 670 million light years since Big Bang.
Yeah.
And then you mentioned our models. So some
Yes.
people have good models and others have really bad models. So maybe you're looking for new ideas. your colleagues and other people involved can't quite understand how objects can evolve like that. But what about the recent information that black holes can occur just from the gas collapsing completely? And there's an accumulation way back then, just after the Big Bang. You need to remember, it was much denser. Gas was obviously made first. Is that right? And then these galaxies, these smudgy blue and red galaxies, are quite small, aren't they? From the next thing I've noticed in the zoo universe, they're not like a spiral, like the enormous galaxy. So when they come together, 670 million years might be just enough time to form these things. So it's your model, there's a concept missing here, isn't it? Is that to do with the size of the observable universe, or is that to do with the mathematics, the physics? Is that why you're not sure about the model?
So,
How you feel?
kind of both. So one, I said there's ways people have tried to solve this. So one of them is direct collapse black holes, so basically when you grow a black hole, you have to assume what we call a seed mass. And if you go through stellar evolution, the star dies, explodes, falls into a black hole. The black holes you form from this, they're quite tiny, and that's why it takes a long time to grow them. Direct collapse black holes can start off much bigger, and this cuts out the stellar bit. You go from a big gas cloud, instead of collapsing down to a star, you go all the way to a black hole. And this creates much bigger seeds. The problem is that still doesn't fix it. That alone, with our models of their accretion, it still, for the most massive black holes theoretically from direct collapse black holes, still doesn't fix it. You have to have a better accretion model, and our accretion model isn't great, so we have something called the Eddington limit, and that says you can't throw infinite amount of stuff onto your black hole. It will kind of start to chuck stuff out, and there's this like equilibrium. But the way we model that is we assume the spherical cow, we assume it to be spherical accretion, and I just showed you endless pictures of an accretion disk, so already that's just not a great assumption. That's done for computational and mathematical ease, and we assume it's pure hydrogen that's going onto this black hole, which again is an assumption. So there's different accretion models, like Bondi-Royal accretion is quite popular, and that tries to be less simple, kind of more complex. And if you combine that accretion with direct, you can get quite close, but even then it's a struggle, I believe. I don't know if I have a slide on this. Well, it's sort of, that kind of tells. So stellar, this is like black hole mass. This is what you get from a stellar and then this is what you get from direct collapse. And then Eddington Limited is our basic model. Super Eddington is this idea that you can go above this model, this limit for like brief periods of time, which is the green. And then, so you can see that even you can get there, but you have to like employ a lot of these different things. And so it's not simple, and physicists like one simple, this is how it happens, rather than saying, well, if it was direct collapse, and it went through super Eddington for a long time, and it had this different accretion physics, and it formed really close to the black hole, then maybe you can just about make up these, but no one's got like a nice answer yet. But I think we're getting there, especially with JWST. It's discovering loads of these early massive black holes, and the more data you have, the more constraints you can put on these different models and rules them out.
Thanks very much. That explains it.
Yes. You work a lot with observations of quasars. Some of the videos I watch on the internet talk about the Hubble tension, where there's a contradiction in the value of the Hubble constant from whether you derive it from the cosmic wave and microwave background or measurements of distant things like quasars, suggesting there's either problems with the measurements or problems with the models. Do you have any sort of opinion on that whole thing?
Yeah, so personally I don't have a opinion. I think they've done so many. The simplest answer was just there was a problem with one of the experiments, right? That they were off. But we've done so many high precision measurements from both. So it's the local compared to the distant universe, and you get a different. It's like a crazy number of sigmas now, different. Like it's very statistically significant, the difference. So I think people have stopped thinking it's just an issue with the instrumentation, because we've got multiple instruments saying the same thing. So I think, for me, an obvious thing would be that there's an evolution, that the Hubble constant is intrinsically different in the local universe compared to the distant universe. Why that would happen is it would be due to more complex cosmological models, which I'm not too familiar with, but I know that there's a lot of problems with cosmology as well, like people don't know what dark matter is. I went to a talk on fuzzy dark matter is a thing now that people are testing, and whether our models of gravity don't quite work either, so there's people at Newcastle doing modified gravity theorems, and I think they've been trying with gravitational waves. But annoyingly, the measurement, the error bar was so large, it covered both values. So again, maybe in the future with gravitational waves, that's another independent measure that could help. But for me, the easiest answer is maybe it must just be evolution, but that's it. That's more cosmology, so don't take my word for that.
Thanks.
Okay, no more questions. You made a Glasgow reference in there. I don't think you noticed what it was. The spherical cal was in a paper about thermodynamics written by Lord Kelvin. So that's where spherical cal comes from. I was taught that in the Kelvin lecture at Glasgow University. So I've got one question. It's not really about your research, but you know when you were making that, you made that excellent demonstration of you need spectra to distinguish the different dots. When they were first identifying that that's not a star, that's not a galaxy, did they do that in the visible, or did they go to the radio first to get clues as to which dots they should be looking at spectra for?
In order to, so there's different. So for example, the DESI, it has targeting programs, right? So it targets things that are quasar candidates, and how it decides what's a candidate is you tell it a lot about conditions. So we say it has to be like a point source, it has to be very luminous, its colours have to be in the optical quite blue, which again biases against my work, but typically they're very blue. And then there's infrared diagnostics, they're very powerful, the quasars, so they have very, very specific infrared colours compared to stars and galaxies. And because of the heated, like this dusty torus gets heated up by the accretion disk, emits in infrared, and this is a very distinct signature. And then equally you can use X-rays, so the black hole, because it's very active, it also has a lot of X-rays, like a lot more than a star or a galaxy would have. So a lot of people search for, they have some condition on it has to be this bright in the X-rays, and if it's that bright, it probably is an active galaxy, and then they'll follow it up with spectroscopy. Doesn't mean 100% of them are, because you get, the universe is full of complicated things. There might be some different exotic things that appear quasar-like, but are actually a star. But that's kind of how you target. So like in my targeting program, because I have to be a bit more relaxed when I this blue colour, which is very good at selecting quasars, I get like 75% of them turn out to be quasars, and I get quite a lot of contamination from red galaxies that they're just bright red galaxies, so they kind of look like red quasars, and that's kind of the problem I have. So yeah, there's other wavelengths you can use to target things that stars fall into this colour space, quasars fall into this colour space, and hope for the best that you get a high fraction that you actually want.
Okay, thank you. Any last questions? No. So could we please thank Vicky again for the excellent remember the next two ASG events a week today on Zoom, if you remember, you get an email about it, is the imaging group meeting about the Dwarf 3 telescope. And then on Saturday, the 4th of October, 2 to 6, we have our open day up at 10, which all are welcome to in the world.